Okay. Thanks very much. So I started just by putting some stuff on the board to talk about before we start. Just kind of a plan of what we'll do. So this is the material we will cover. So today we'll talk about existence of finite geodesics. So this one here means lecture one. And then we'll move into infinite geodesics. And we'll spend most of the lectures talking about infinite geodesics. And the main questions will be, how many infinite geodesics are there? Specifically, how many edge disjoint infinite geodesics can you find? So that will, that question will come out through all the lectures. And then another main question is these infinite geodesics, do they have asymptotic directions? And that will be covered mostly in lectures 2 and 3. So here are the main references for the material. I think this stuff on existence of finite geodesics you can find in the book 50 years ... at the beginning of chapter 4. And then also this material is also pretty much in the book, but here are the main papers to look at. There's a paper from Newman in '94, which he wrote as part of the ICM. I think it's called A Surface View of First Passage Percolation. Then Hoffman has two important papers in '05 and '08. Forget their names exactly. And then last paper I wrote with Jack in 2014. Okay, so there are a lot of topics within geodesics, so we're not going to cover a lot of stuff. So this is a partial list of things we won't cover. They're all important. Geodesic wandering, how far do geodesics stray from straight lines? There's a whole theory of basically everything we'll talk about in last passage percolation. Won't say much about that. Then there's a uniqueness of infinite geodesic question. If you have two infinite geodesics, or if you fix a direction, can you find two infinite geodesics in that direction? We won't say much about that. Bigeodesics are doubly infinite geodesics. There's a lot of work on those. Won't talk about it. There's a famous midpoint problem, which says if I look at a geodesic between 0 and the point NE1, does it come close to the point N/2E1, the midpoint? This was recently solved by Alberg and Hoffman. Won't talk about it. And then we have many variants of first passage percolation. There are tons of models out there that are similar. A lot of them are introduced in order to overcome some of the obstacles in first passage percolation. For instance, Euclidean first passage percolation is a model which is built on a Poisson point process. And so because the Poisson point process is rotationally invariant, the limit shape for that model has to be a sphere. So you automatically know the limit shape. Anyway, there are many different models. Last passage percolation, as I mentioned, there are models that are related to PDEs that, anyway, we won't mention. Okay, any questions on the plan here? Good? Okay. All right, so let's start with finite geodesics. Okay, so to start from the beginning, let's give a definition of a geodesic. So a path gamma from x in ZD to y in ZD is a geodesic if the passage time of the path is equal to the passage time between x and y. So it attains the infimum. Okay, so directly from the definition, you can check that a segment of a geodesic is a geodesic. Of course, it's between two different points, but it's a geodesic between its endpoints. Okay, so this is an important point for the definition of infinite geodesic later. Okay, first question. Do geodesics exist? Okay, so to give the result on, well, this question is not completely solved. There are some open parts to this, some open cases. But to talk about the cases that are solved, we'll introduce a random variable, which I'll call the passage time to infinity. So that's our next definition. This appeared first in a paper of Zhang from like, it's a bit unclear when this paper was written because I've seen anywhere between 94 and 98. It's called double behavior of critical first passage percolation. So this is the passage time to infinity. Okay, so we're going to let rho of x equal the limit n goes to infinity of the passage time between x and the boundary of the box of size n. So here, Bn is minus nn, oops, minus nn to the d, and then his boundary Bn is just the set of x in Bn, which are adjacent to the complement. So there exists a y in Bn complement such that x minus y is 1. Okay, so the picture for this, we have a box, here's 0, Bn. According to this definition, for small n, x may be outside the box, but for large n, it will be in the box. So here's x. You take the optimal path from x to the boundary. Okay, so the first question is, does this limit exist? Well, as long as x is inside the box, it's more difficult to get to the boundary of the box of size n plus 1 than to the boundary of the box size n. So this sequence is eventually monotone. So this limit exists by, I guess I'll say, eventual monotonicity. Okay, so this is called the passage time to infinity. There is an alternative characterization, which is important, and I'll give it as an exercise. So I'll write a lot of things like check something or exercise. Some of these will appear on the problem sheet. I think this one does. So you can show that rho x is equal to infimum of T gamma over all paths gamma, which are infinite, edge self-avoiding, path started from x. Okay, so take all paths which start from x that are infinite, go out to infinity, and take the minimal passage time one. Now, of course, this will often be infinity. So, but in some cases, you'll get a finite limit. Anyway, this is equivalent to this definition over here. Okay, so here's the main proposition about existence of geodesics. I have 3 parts. The third part is an exercise. Okay, so if, so I'll put first, this is just a deterministic claim. So fix any passage time configuration that you want. So if rho of 0 is infinity, so the passage time from 0 to infinity is infinite, then I'll put in quotes, geodesics exist. So I mean by that for every x and y in ZD, there exists a geodesic from x to y. Okay, so this is a sufficient condition to get existence of geodesics. It is not necessary, but it's sufficient. Okay, number two, well, then the question is, when is rho 0 infinite? Well, if our edge weight's TE, if this is IID with probability that TE equals 0 less than PC, where PC was defined, I guess, yesterday by Riddhi, just the threshold for ordinary Bernoulli bond percolation, then almost surely rho 0 equals infinity. Now this number two, you could actually prove probably directly from the shape theorem, although we're not making any moment assumption here. So you have to use some more souped up version of the shape theorem that requires no moments. But we're going to just prove it directly without the shape theorem. Okay, so if you put 2 and 1 together, you get that if probability TE equals 0 is less than PC, then geodesics exists almost surely. Okay, and then part 3. So this is just an exercise. If the TEs, if the collection is IID, and I'll say with continuous common distribution, so that is, you look at the marginal of one of them. If that's continuous, then almost surely for every x, y, and ZD, there exists a unique geodesic from x to y. Okay, so continuity gives you uniqueness. It's probably equivalent, I would guess. Yeah, I think probably equivalent. Well, I guess if you have common distribution which is continuous, then you can't have an atom at 0. So then probability that it equals 0 will be 0. Any other questions about the statements here? No? Okay. So we're not going to prove 3, but we'll prove 1 and 2. So let's start with proof of 1. Okay, well, we have to assume that rho 0 is infinite. So let's suppose rho 0 is infinity. Okay, so the first thing is that we take any other vertex, if x is in ZD, and we look at the difference between passage time from 0 to the boundary of the box of size n, and the passage time from x to the boundary of the box of size n. Well, just by triangle inequality, it's bounded above by t0x, and that's some finite number. So if this term is going to infinity, then this term goes to infinity also. So this gives us that rho x is infinite for all x. Okay, so we have to show that there's a geodesic from x to y for any x and y. So let's fix x and y. Okay, so what's our picture? We have x, here's y. Well, we can fix a deterministic path. I mean, everything's deterministic. So let's just fix a path going from x to y. It doesn't have to have minimal length or anything. So let's just choose gamma from x to y. Here's gamma. Okay, well, we know that Tx boundary Bn is going to infinity. So we can choose an n which is so large that the passage time from x to the boundary is bigger than the passage time of this path. So let's fix n such that two conditions hold. First of all, x is actually in the box of size n. And second, the passage time from x to the boundary of the box of size n is bigger than the passage time of gamma. So maybe 0 is in here somewhere. I don't know. There's 0. Here's box of size n. Okay, this is allowed. Okay, so now let's consider any path that starts from x and leaves the box. So if we take gamma prime, starts at x and exits Bn, I don't know, something like this. Let's say it goes to y. It doesn't really matter if it goes to y or not for the arguments, but anyway, it's going to exit the box. Well, then we look at the passage time of gamma prime. Well, it's greater than or equal to the passage time of the initial segment from x to the boundary of the box, right? And that segment may not be optimal. So we get greater than or equal to Tx boundary Bn. But by choice of n, that was bigger than T gamma. So that's strictly bigger than T gamma. So this means that gamma prime cannot be optimal. Right, but now that restricts us to finitely many paths in the definition of the passage time. So the infimum is over finitely many paths. And so there exists a minimizer. It doesn't have to be gamma, but there has to be a minimizer. Okay, any question on that argument? So this is a simple condition to guarantee existence of geodesics. Okay, so let's move on to part 2, which is that if probability t equals 0 is less than pc, then rho 0 has to be infinite almost surely. Okay, well, our assumption here, so we're going to suppose probability t equals 0 is less than pc. Well, we know the distribution function of TE is right continuous. So we can choose a delta positive such that probability TE less than or equal to delta is also less than PC. Okay, well, but this means now that if you look at all of the edges which have weight less than delta, they cannot form infinite paths, right? Because their probability is less than PC. PC is the threshold for existence of infinite components, right? So we get from this, then almost surely there is no infinite path whose edges have weight less than or equal to delta. I gotta go down here. Okay, so the claim from this is that then each infinite edge self-avoiding path from 0 must have infinitely many edges with weight bigger than delta. Okay, and the reason is that if we start from 0, we have an infinite path here. If this were not true, then what would be the case is that there would be finitely many edges with weight bigger than delta, right? So there would be a final one here. Here's the last one. But beyond that part, beyond that point, you have an infinite path with weights less than delta. But that's not allowed, right? Because what we said over there. Okay, so now if we look at the alternative characterization of rho 0, well, it's the infimum of T delta over all such paths. But they all have infinitely many weights bigger than delta, right? So that means that they're all infinite. And so this gives us that rho 0 is infinity. Okay. I guess I should be putting some almost sureles somewhere. So this should be almost surely. This should be almost surely. Maybe I'm missing almost surely down there. Nope, we got it. Okay, any questions on that? Yes. Yeah, so what we would like in this argument is to have the edges which have weight less than delta to not percolate. So we want them not to have infinite paths. So in order for that, we need that the probability to be less than delta is less than the critical probability for percolation. Because if this were bigger than the critical probability, then we would get infinite paths with this condition, right? If you imagine that an edge with TE less than delta, we just call that an open edge. Right? So then the probability to be open is less than PC, so there can't be any infinite open paths. Anything else? Okay, this is basically what we want to say about existence of finite geodesics. I have some remarks about cases that are known and cases that are not known. So the proposition says that if F0, where probability T equals 0 is less than PC, then we have geodesics. That case is solved. That's the end of the proof. Okay, some remarks. Okay, first of all, this argument shows that if probability T equals 0 is less than PC, then rho is infinite. But even more is true, as we know from the shape theorem, or under no moment assumption at all, Krishnan has shown that passage time has to grow linearly. It's not just infinite, it has to grow linearly. So if probability T equals 0 is less than PC, well, then we get probability that the lim x in ZD, x goes to infinity, of T0x divided by norm of x is positive is 1. So if we go to infinity in any direction and look at the passage time divided by norm of x, that's positive. This is says that the passage time is linear at least. We don't need any moment condition for that. So this is done by Krishnan. And it's part of this, this characterization of the time constant being positive that was mentioned yesterday. It's part of the proof that if probability T equals 0 is less than PC, then the time constant is positive. So in the exercises, I gave an exercise to prove this when probability T equals 0 equals 0. That part, that's doable, somewhat difficult, but doable. This one is more difficult and actually may have been in the exercise. Is that right? No, okay. Too hard. Okay, yeah. All right. That makes sense. I mean, it's difficult. Okay, so that's just a comment about part 2. Okay, second, then the question is, do geodesics exist when F0 is greater than or equal to PC? So the probability that T equals 0. Okay, well, there was a result by Riemann and Re I'm not sure how to pronounce that, but okay, the answer is yes when dimension is 2. I think this was done in like in the 80s or possibly earlier. 78, yeah, okay. So quite early. Yes. It is not, no, because, yeah, so the question was, is rho 0 equal to infinity equivalent to existence of geodesics? And it's not true, because if you look in this case, let's say in the Riemann and Re result here, states that in particular, if F0 is bigger than PC strictly, then you have geodesics. But when F0 is bigger than PC, then there are infinite zero paths. And once my box becomes big enough over here to intersect one of the infinite zero paths, then I can just go to infinity for free. So rho will be finite in that case. So that's an example where rho is finite, but you have geodesics. So it's not equivalent. Okay, so this was maybe the first result. Next one, Zhang showed. The answer is yes, if F0 is bigger than PC. Okay, so the only possible exceptional case where you may not have geodesics is the case where F0 is exactly the critical value. And as far as I know, the only result in that direction is by Eric Bates, which states that the answer is yes, if D is at least 3, F0 is PC, and also F of H is PC for some H positive. Okay, so such a distribution looks like this. You have an atom at 0 of size PC, and then you have to have a gap between that and the rest of the support. So the edge distribution will look something like this. I guess this will be like the density or something. But anyway, there should be a gap. Okay, so whenever this is true, then there's an argument that you have geodesics. So the remaining case is that F0 is PC, there's no gap. Any questions on any of that? Good question. I guess I would believe that they just always exist in ZD. Yeah, so this is part of the exercises. Yeah, so I gave a few different problems to construct examples where geodesics don't exist. Yeah, so in kind of progressively more difficult scenarios. So. Okay, so that's what we know as far as I know. Okay, so I'll just mention two other results on finite geodesics before we move to infinite geodesics. So this would be remark 3. You could ask how long are finite geodesics? How many edges are in them? Now, there are many different results in this direction. You can bound the expected value of the number of edges in a geodesic. You can bound the expected value of the number of edges in the union of all geodesics between 2 points if you don't have unique geodesics. I'll state a result that I proved with Tuka, Elfinger, and Jack. So if F0 is less than PC, the reason why I state this result is I think it has the minimal assumptions for a result on upper bound on the length of geodesics. So if F0 is less than PC, then there exist C1, C2, such that for all x, probability there exists a geodesic from 0 to x with at least equal to C1x many edges is bounded by C1 e to the minus C2x. Okay, so you have very small probability to have a geodesic which has length, a number of edges larger than constant times norm of x. So I would write this as a geodesic length is linear. Of course, to get any path from 0 to x, you need at least x many edges. Okay, so this is the upper bound. Yes? This and Keston's result. Yeah, so Keston's result, I guess you're talking about the fact that if F0 is less than PC, then there exists a positive such that the probability that there exists any path starting at 0 with n many edges, but passage time less than an is bounded by e to the minus constant n, i.e. lemma 5.26 from aspects. Yeah, so that tells you that very long paths have high passage time. But in order to get a geodesic length upper bound, you have to show that you have to combine this with a passage time upper bound between 0 and x. And in order to do that, you normally need a moment condition. But this result does it without any moment condition. Okay, last remark about this. This would be remark 4. So when is rho 0 finite? Almost surely. So is there a condition that tells you, given the distribution, if rho 0 is finite? Well, or infinite. So this here, number 2, says that if F0 is less than PC, then rho 0 is infinite, and therefore rho x is infinite for every x. But that's just a sufficient condition. Is there a necessary condition as well? Well, there is in 2 dimensions. So by me and Ykit Lam and Xuan Wang, so in dimension 2, we have that rho 0 is finite almost surely if and only if the sum over k of the inverse distribution function evaluated at 1/2 plus 1/2 to the k is finite. So this F inverse is just the inverse of the CDF of one of the edge weights distribution. Of course, the edge weight distribution may have atoms or flat pieces, in which case you can't directly define an inverse. So this is like a generalized inverse. It's the one you normally use in like graduate probability when you try to define a sequence of IID variables as push forwards of the inverse distribution function of the distribution of those random variables applied to uniform IID random variables. So anyway, that's the result. Any questions on that? So if you're subcritical, you mean the result over here that that if probability t equals 0 is less than PC, then rho is infinite. Can you see that from this sum? It'll be below that eventually. Yeah, so I think, yeah, that's right. That if you look at 1/2, so you have your distribution, maybe you have an atom here of size, I don't know, p, which is less than 1/2. And then you look at the point where the distribution function is equal to 1/2. I don't know, it's some value here. So maybe the CDF looks like this. I don't know. Here's the CDF of one of the edge weights. And here is the point where we get to the value 1/2. And now if you consider this sum, F inverse 1/2 plus 1/2 to the k is always to the right of this point. Right, so all the terms are bigger than this. So the sum is infinite. That is true. Yeah, so.
Why is that not infinite?
From this condition here, you're saying?
In all dimensions, why is that not?
Oh, in all dimensions. Yeah, well, it just hasn't been proved. I mean, So the exceptional case is where F0 equals PC.
Okay.
So that case is special because you're not subcritical. So you don't have very small zero clusters, but you're also not supercritical. So you don't have, at least it's conjecture that you don't have infinite zero paths. And so, yeah, it stands apart from the other two cases, and none of the proofs work. Like if you try to run this proof over here to get, don't get a delta. Yeah. Yeah, you need a little bit of room here. And I haven't presented the proof for supercritical. So, but you can see at least why this doesn't work in that case. Anything else? Okay. Oh, yes. Yeah. Yeah. So on general two-dimensional lattices, you would replace this with PC. Yeah. So I also haven't explained this at all. I mean, this is a long proof, so we're just omitting that. And this is just a statement of the result. Okay. So let's move on to infinite geodesics. As I said before, there's still a lot you can say about finite geodesics, but we're going to not do that. Okay, so for the definition of infinite geodesic, well, you can't really take the same definition, right? Because if you try to take an infinite path, which has minimal passage time, well, there are infinitely many paths, they have different endpoints. Paths generally will have infinite passage time. So what's a what's a minimizer? So instead we use that perturbative remark afterwards, which said that if you had a finite geodesic and you take a segment, it has to be a geodesic. So that would be a definition in the infinite case. Here's the definition. An infinite path is, let's say, I even need to introduce a symbol, probably not, is an infinite geodesic if each of its segments is a, I'll put in parentheses, finite geodesic. I guess I don't really need to even say finite because geodesic was defined as a finite geodesic. Okay, so the first question about infinite geodesics, how many are there? Is there even any such thing? Of course, you can make any definition you want. It doesn't mean that that thing has to exist. So for an outcome, omega, which, I guess is our passage time configuration, we're going to let n of omega be the following thing. So as the supremum over all k at least 0, there exists k edge disjoint infinite geodesics. Okay, so looking at your passage time configuration, find as many edge disjoint infinite geodesics as humanly possible, and that is that's n. Okay, so here's the first proposition about how many are there. So the question of how many are there is the question of what is the value of n. So if the distribution of TE is translation ergodic, for instance, if TEs are IID, then n, which is n omega, is almost surely constant. Furthermore, if geodesics exist, in the outcome omega, then n omega is at least 1. So when I say if geodesics exists, I mean if between any two points, there's a geodesic. Okay, first of all, this variable n, this would be a check or exercise or something, that n is measurable. Okay, also observe that if I take any passage time configuration, I find the maximum number of geodesics, infinite geodesics, then I shift that passage time configuration, all the geodesics just shift, right? So the maximum number of edge disjoint geodesics remains the same. Also, n is translation invariant. Okay, well, any measurable function is translation invariant is going to be almost surely constant if you assume that this underlying distribution is translation ergodic. So this gives us that n is almost surely constant. I'll just stress that it's very important to check measurability whenever you do this. I've seen tons of papers where this is not checked. Of course, no one checks it, so but you should check it. There's some interesting examples of random variables that are not measurable. They seem like they would be. They're translation invariant, but they're not constant. Okay, so that's the first part. Next, we need to show that if geodesics exist, then n omega is at least 1. So for the second claim, we're going to let gamma n be a geodesic between 0 and any 1. Okay, we can do that for every n because we have geodesics. Here's my picture. Here's any 1. Here's my geodesic gamma n. Okay, so we have a sequence of geodesics. They all start from 0. Each of them has to take some first edge, which comes out of 0. There are only 2D many edges coming out of 0. So one of them has to be the first edge of infinitely many of these paths, right? Just like some pigeonhole or something like that. So we can choose F1 that is the first edge of infinitely many of the gamma n. Let's say we can make a subsequence. Let's say some subsequence gamma n k's. They're all going to take the same first edge. So let's say they're all going up first. Here's F1. Okay, now look at the sequence gamma nk. They all take the edge F1 first. They have to take a second edge. It has to be one of the edges coming out of the second endpoint of F1. So then we can choose F2. That is the second edge of infinitely many of the gamma nks. And maybe that one goes to the right. I don't know. There's F2, and so on. Now we just repeat this procedure over and over. This is really a diagonal argument. Right, so repeat to produce the sequence F1, F2, F3, and so on. Okay, these are all connected to each other. They form a path, infinite path, and you can check the path following F1, F2, and so on is an infinite geodesic. Okay. Because any finite segment of it is going to be contained in one of these finite geodesics, but segments of finite geodesics are finite geodesics. Right? Okay, any question on that? I think this is just like a brute force compactness argument. You could rephrase it more abstractly so that you just apply compactness. Yes?
Can you actually think of plots as being in some complex space?
I think so. Yeah, I think that's possible that you could just define a space of paths with a particular metric, and then use compactness. I guess this is like actually a proof that that space is compact. Okay, so this argument is, I would say, more or less trivial. I mean, you got to do something, but it's you get that n is at least 1 whenever you have geodesics. The main question is whether n is at least 2. And that turns out to be significantly more difficult. I mean, I think it was unknown until 2005, around then. Although I think technically it may have been proof for exponential distribution earlier. But it's formulated in terms of competition models. Oh, I don't even know what time. So when did I start? 9? I've been going for 45 minutes. Okay, that's all right. Okay, so what is the value of n? That's our main question for the moment. Okay, so for simplicity, let's take TE that are IID and continuous. In other words, the common distribution is continuous. A lot of the ensuing arguments don't really require this, but I'll just do it to make it a little easier. Okay, so first of all, there are some results. Hoffman, Marchand, and Hagstrom and Pimantel. Okay, they show that n is at least 2 almost surely. And this is what we're going to be talking about in a minute. There's also a result, Hoffman from 08. N is at least equal to the number of extremal points of the limit shape B. Okay, the limit shape is a compact convex set, etc., containing the origin and having symmetries of ZD in RD. And any such set must have at least 2D extreme points. You can try to work it out, but in 2 dimensions, for example, you have to have an extreme point in the closure of each quadrant. So this gives you n is at least 2D. It could be way more extremal points, actually. But, okay, I only know, I'm trying to think if there's any other example other than the one I'm going to tell you about, which bounds the number of extremal points. So there's a result by me and Mike Hoffman. States that given any number k, there exists an IID continuous distribution of TE in dimension 2 such that n is at least k almost surely. So in 2 dimensions, you can produce edgeway distributions that are IID and continuous and have as many geodesics as you want. As many, but finite number. This is
finite, or do you mean the number is at least a finite number?
At least any given finite number, yeah. But if you want to make it bigger than k plus 1, you got to change the distribution. According to the proof, it really should be that n is infinity, but this is what it says. Now you can consider this problem for non-continuous edge weights, in which case you don't have uniqueness of geodesics. And then the problem becomes related to what's called the geodesic graph of the origin. And the analogous question is, how many topological ends does the geodesic graph of the origin have? And the arguments in this paper show that there exist IID non-continuous distributions for which there are infinitely many topological ends of the geodesic graph. From that, you can get this result by some approximation argument. Yes? Extremal point, yeah. So what is an extremal point? I think it's like, it's a point in your convex set such that it is not on the interior of any line segment joining 2 points in the convex set. Yeah, so it's, you know, if you look at some examples like, look at the square convex set and look at this point here. Well, it's on the interior of this line segment, not an extremal point. But if you look at the circle, every boundary point is an extremal point. Because if it's on the interior of a line segment, well, the 2 points, at least one of the 2 points has to be outside the convex set. So there are various different kind of weird definitions for convex set. This is one extremal point. There's something called exposed point, which is actually somewhat different. Anyway. The way that he phrases it in his paper is n is at least equal to the number of sides of the limit shape. Because if you have a limit shape which is a polygon for some reason, then the number of extremal points equals number of sides. Okay, so these are the results that I know of. So we're going to spend, I'm not sure if we will finish it today, but we'll spend the next chunk of time discussing Hoffman's argument that n is at least 2. Here's the idea of Hoffman, n at least 2. Now this argument I think is great. It should be in that book, Proofs from the Book or something, because yeah, it's great. And in addition to that, even though there are other proofs, like Gary-Marchand proves it almost exactly the same result, Hoffman's argument introduced the idea of analyzing Basemann functions for geodesics. And that's what we're going to study for probably this whole time. Okay, so the first task is to introduce a Basemann function and some of its properties. Now, Basemann functions were actually introduced like in the 30s or something by Herbert Basemann. And he has this book, Geometry of Geodesics, which is quite interesting. So it's an object which is defined in general metric geometry, but you can define it in first passage percolation. And I should say that before Hoffman started analyzing these Basemann functions, there were in the papers of Newman from earlier, he considered not exactly Basemann functions for geodesics, but a similar type of thing, which maybe I would call a Basemann limit or something, which turns out to be the same thing if, it turns out it should be the same thing. I don't think there's any proof of that, but. Right. So let's let gamma be an infinite geodesic with starting point x0. And vertices x0, x1, x2, and so on in order. Okay, for x and zd, we're going to let b sub gamma of x equal the following limit. Limit n goes to infinity, tx xn minus tx0 xn. My memory is that the actual definition of Basemann function from metric geometry is the negative of this. Not totally sure why I wrote it this way, but. Okay, so the picture here is we have x0, here's my infinite geodesic, here's x1, and so on. Xn is down here. And then we have x somewhere. X could be on the geodesic, I don't know. And now we look at the difference of passage time between both of these 2 points to xn. So we ask which one of them gets to xn first, and by how much. Okay, so let me move down here. Oh, yes. Oh, I see. Yeah. So it's the limit as n goes to infinity of txxn minus tx0xn. So you look at the passage time from x to xn here and subtract the passage time from x0 to xn. Yeah, does that, yeah, it's sort of hard. Txxn minus tx0xn. Okay, so b sub gamma is the Basemann function, or possibly as negative Basemann function for the infinite geodesic gamma. Okay, so question number 1, as usual, like I said, you can define anything you want, it doesn't have to exist. We have to check that it actually exists. Limit exists. Well, it turns out that the sequence is monotone. So if we look at txxn minus tx0xn, well, the passage time from x0 to xn, if you can look all the way down there, maybe I'll reproduce the drawing here. There's x0, there's xn, and x is over here. Now the passage time from x0 to xn is just the passage time from x0 to xn minus 1 over here, plus the passage time from xn minus 1 to xn. That's because the passage time is additive along a geodesic because segments of geodesics are geodesics. Okay, so the first thing is, well, we're going to keep xn the same, but then write this as x0, xn minus 1 minus tx0, xn minus 1, xn. That's just from additivity along the geodesic. And now we're going to use triangle inequality for the first term, bound above by tx xn minus 1 plus txn minus 1 xn, and then keep the other two terms the same. tx0 xn minus 1 and okay, txn minus 1 xn. So this is just triangle inequality. That's even readable, probably not. Triangle inequality for that one. Now the txn minus 1 xn's cancel out, and you just get tx xn minus 1 minus tx0 xn minus 1. Okay, so the nth term is less than or equal to the n minus first term. So the sequence is monotone, non-increasing, and the limit will exist as long as the sequence is bounded, right? But the sequence is bounded just by triangle inequality. So since we have tx xn minus tx0 xn less than or equal to tx x0, which doesn't depend on n, the limit exists. Okay, so this is a very special property of geodesics. We can't do this with any other path because we have to have this additivity in the first step. Yes?
I've seen Riemann functions defined as a bivariate function where you take a sequence of points and compare the distance to that point. Is this somehow equivalent in some way to that, or is it slightly different, but there's a reason for the difference?
Yeah, so I guess two things I can say about that. The first is that for this definition, we will also, in just 1 second, define it as a function of 2 points. The second thing is that the same as the thing you're talking about, which is the difference of passage time to a sequence of points receding to infinity? Well, it should be. And there are various cases in which it can be proved that it is true. The issue is that your sequence doesn't reference any geodesic. Right? This is a Basemann function for geodesic. This is the actual definition of Basemann function. You need a geodesic. The question is whether your thing is the Basemann function for some geodesic. Well, it can be proved in some cases if you know uniqueness of geodesics in certain directions and some limit shape boundary differentiability assumptions. But that's a difficult problem, I think. And what you're referring to was introduced by, or I guess in FPP by Newman, but now is used a lot. Okay, so that's Basemann function. We're also going to define, as you were saying, the bivariate one. So we define b sub gamma xy to be b gamma x minus b gamma y. Okay, if you look at the definition of b gamma x over there, way down at the bottom, when you subtract these two, the term tx0 xn will cancel out. And so you get basically what you said, except the sequence of points is going to infinity along the geodesic. Okay, so let's give some properties. Okay, A, we have that b gamma xy in absolute value. As I said, when you write out the definition, one of the terms cancels, and you just get that it's the limit, n goes to infinity, tx xn minus ty xn. And then you can just apply triangle inequality to get that this is bounded above by txy. Okay, so the bivariate Basemann function in absolute value is bounded by the passage time. Okay, property B. For m less than n, if I look at the Basemann function from xm to xn, so in the picture here is x0, xm is here, xn is here. Well, this is going to be the limit, capital N goes to infinity, t xm x capital N minus t xn x capital N. At some point, sequence x capital N going to infinity. Now the passage time from xm to x capital N is just the sum of these edge weights, right? Then the passage time from xn to x capital N is the sum of these edge weights. So when you subtract them, these terms cancel. You just get the passage time between these two. So this is just equal to t xm xn. In other words, if you look at points on the geodesic itself, Basemann function is just the passage time. Right? We know that it's always bounded above by the passage time, but on the geodesic it's equal. Next property, Basemann function has additivity property. So we look at b gamma xy, it's equal to b gamma xz plus b gamma zy for all x, y, z in ZD. This is just because it's defined as a difference, and you get cancellation again. So in some way, the Basemann function, it kind of behaves like the passage time. Well, on the geodesic, it's bounded by the passage time. Instead of being subadditive, it's additive. Okay, last, property D. If I look at b gamma xy in a particular outcome omega, and let's say I shift the whole outcome to the right or something. Okay, well, then this geodesic is just going to shift to the right. It's going to be a shifted geodesic in the new shifted environment. So this is equal to B T gamma Tx Ty in the shifted environment T omega if T is a lattice translation, or I'll say integer translation. Okay, I mean, the picture is just that. I have geodesic over here. I have my points X and Y. There's gamma. And then I shift everything to the left by some integer translation. So let's shift it all to the left. Everything moves over. Tx, Ty, gamma moves over. Here's T gamma. And I have to compute it in the shifted weights. It's exactly the same computation, right? Because I moved everything over to the left. So the boost function has this nice compatibility with translations. Okay, and last property, this is an exercise. If gamma 1 and gamma 2 coalesce, so that is they have finite symmetric difference. So the picture looks like this. Here's gamma 1, gamma 2 is over here, eventually coincides with gamma 1. So if we're in this scenario, then B gamma 1 xy equals B gamma 2 xy for all x and y. And then I guess we would say the bivariate Basemann function is equal for the two geodesics. I don't think it's true that the actual Basemann function will be the same, because you're measuring passage times relative to different endpoints of geodesics. But because when you take the bivariate Basemann function, that term cancels out, then you can show that they're equal. Okay, so these are the question. Yeah, they're just off by a constant, I think. Okay, so these are the properties. We don't have that much time. Am I supposed to stop at 15? That seems to be what people were doing. Okay, so we'll do a little bit of Hoffman's proof using Basemann functions, and then we'll have to complete it next time. Okay, so let's go to Hoffman. Okay, well, we already know that n is at least 1 almost surely, because, well, geodesics exist because we took a continuous distribution for the edge weights, therefore rho is infinity. So the only way that we could not prove the theorem is if n were just 1. I want to show it's at least 2. So let's assume for contradiction that n is 1 almost surely. Okay, well, what does that mean? It means that you can find a infinite geodesic, but you cannot find two edge disjoint ones. That is, if you take any two infinite geodesics, they have to touch. Right? Okay, well, let's take two infinite geodesics. They have to touch. Now the question is, do they have to actually coalesce? Well, if they don't coalesce, then they have to separate at some point. In that case, what happens is that we can just consider the geodesics from these points onward, and we'll get two edge disjoint infinite geodesics. So they actually have to come back together again, right? They have to keep doing this over and over, coming back and forth. So now if you look at the geodesics between these two meeting points, because segments of geodesics are geodesics, we get two different geodesics between these two endpoints, two different finite geodesics. That's not allowed because we have uniqueness of finite geodesics because the edge distribution is continuous. Okay, so the result of this argument is that if I take any two infinite geodesics, they must coalesce. Any two, so let's say almost surely, any two infinite geodesics must coalesce. Well, that's nice because in the exercise, we have that the Basemann functions are the same. That means that I can just take any infinite geodesic I want, consider the Basemann function, and it doesn't depend on the geodesic that I chose. So we will then arbitrarily, and this is kind of the magic of the proof right here, I think, that because of this assumption and the coalescence property of Basemann functions, it is possible to define this function in such a way that it doesn't depend on the geodesic. So it's just like an observable of the passage time configuration. If you don't assume n equals 1, you can't do this. So we will arbitrarily select an infinite geodesic gamma, and we're going to set f of xy equals b gamma xy. Now, I think an important point here, I'm going to again harp on measurability because I'm insane. So if you just arbitrarily select something in a configuration and make a definition, why does that have to be measurable? You could have done it in such a way that you're using like the Volterra set from analysis 1, you know, and then make your definition that way. It doesn't have to be measurable. So it's important that this thing is measurable. That's an exercise. That one is actually a somewhat interesting exercise. I mean, the other one, n being measurable, maybe less interesting, but this one is more interesting. F is measurable. Hoffman does not check this, no, but I think it's important. It's true. He must know that it's true, but yeah, some of the, often these arguments are not given. So, but anyway, it's an important point. Okay, we're almost done. Let me just state one property. Yeah. Okay. Also, we look at expected value, fxy. Well, fxy is a Basemann function. Basemann function is bounded in absolute value by the passage time over here. So it's less than or equal to expected value txy. Because we assume finite mean for the passage times, we don't really need that much. We could just have the existence of the first moment of this y variable from the first lecture. Anyway, because of that, we get that this is finite. So that means f has finite first moment. We're going to want to apply the ergodic theorem to f. So we need to know that f is measurable, very important, and that it has finite mean. Okay, so we will continue that next time. Okay, thanks.